Okay, so for today's quick seminar, we are very pleased to have Professor Urmila Mahadev from Caltech. Professor Mahadev did groundbreaking work on quantum protocols involving a single untrusted server, and this has led to many very interesting follow-ups during the last few years. So I will turn it over to Urmila.
Thanks, Carl, and thanks for the invitation. I'm happy to be here, even though it's virtual. So my talk is on classical homomorphic encryption for quantum circuits. This is a topic that lies in quantum computing and classical cryptography, and my goal is to keep it at a high enough level so that everyone can follow, but please feel free to stop me during the talk and ask questions if there are things you don't understand. I did leave a lot of room for questions, so I don't have that many slides. Okay, so I'll get started by telling you what homomorphic encryption is. Here's the setting. Let's say there's a quantum computer on the cloud, and you only have access to your classical laptop. So what you'd like to do is use the computing power of a quantum computer without leaking information about any of your data. So what you'd like to do is, let's say you have some data. You want to classically encrypt your data and send it over to the quantum computer on the cloud. And then the quantum computer should be able to compute a circuit U on top of this encrypted data. So what this means is he sends back the encryption of U applied to your data M. Now this is, when I say he's applying U on top, I'll refer to this as saying he's homomorphically applying the unitary circuit U to the encrypted data. So that's where the word homomorphic comes in. And the question is whether this is possible, whether it's possible for a classical computer to send over encrypted data, for the quantum computer to compute on top of that data, and the whole time, since the data is encrypted, the quantum computer learns nothing about the data of the classical computer. That's the question of quantum homomorphic encryption. Now, in the classical setting, this question has been studied extensively, and the model is slightly different. Now here you have—
It's a simple question. So when you say, so there are like kind of two things that we may want the quantum computer not to learn. Like one is kind of maybe the, maybe it doesn't even make sense. So there's you may not want them to know that the unitary that you're applying, but also maybe the state. But now that I think about it, there's no state. So I guess you don't want them to learn anything at all, right?
Yeah, no, you're right. Okay, so there are two pieces of information. There's, let's say the input state is this message M, which we're assuming is a classical string. And then the circuit that's being applied is this unitary U. So in an ideal case, he wouldn't learn about either. However, there's an easy way of just getting rid of U. So instead of U, I'm going to assume that the quantum computer is always applying a universal circuit. And what a universal circuit is, it's a normal circuit, but each gate has kind of a control wire. So basically the input specifies the description of the circuit. So now all we need to hide is the input M. Okay, great. So just, I forgot to mention one thing. In this setup, the classical machine is referred to as the client, and the quantum machine is referred to as a server. So the client wants to delegate a computation to the server, and the server should be able to homomorphically apply the computation. Okay, so now let's go back. This question has been extensively studied in the classical world, so let me tell you what's been done there. Now in the classical world, the client is still a classical machine, but now the server is a much more powerful classical machine rather than a quantum machine. So now you have a relatively weak classical machine wishing to delegate a computation to a much more powerful server. And now the setup is the same. The client is supposed to send over some encrypted data, and the server is supposed to be able to homomorphically apply a classical circuit, let's call it C, on top of the data. In a breakthrough result by Craig Gentry in 2008, this was first shown to be possible, and since then it's initiated a lot of follow-up work in the classical world. And once we know that a classical homomorphic encryption scheme is possible, the most obvious question is, can we just use these classical homomorphic encryption schemes directly to homomorphically apply quantum circuits rather than classical circuits? So in the picture I just showed you, the server was homomorphically applying a circuit C to the encrypted data. Do these classical homomorphic encryption schemes just immediately work for quantum circuits? So can the server homomorphically apply a circuit U rather than a circuit C? This question runs into immediate difficulties because there's a fundamental property of classical homomorphic encryption schemes which seems to conflict with quantum computations. This property is that in a classical homomorphic encryption scheme, each bit has many different encryptions. The encryption is probabilistic. So the reason intuitively this is necessary is because let's say the encryption was deterministic. So there's only a single encryption for each bit B. Now, since the server can homomorphically apply many different circuits, what he can do is he can take his input, apply a bunch of different circuits to it, and then compare the outputs and see if they're different or not. And by comparing the outputs, he could potentially learn something about the input to the circuit, which was supposed to be secret. However, if the output encryptions look different, so for an output 0, there are many different encryptions, then this kind of comparison cheating strategy makes no sense. So this is why it's necessary. Now let me tell you why it presents a problem in the quantum setting. And this has to do with the quantum property of interference. So let me first remind you what that is. And to do that, I should tell you what the Hadamard transform is. The Hadamard transform is just a quantum Fourier transform. It's a reflection by pi by 8. So it maps 0 to uniform superposition over 0 and 1. And it maps 1 to uniform superposition over 0 minus 1. Over 0 and 1, but there's a phase in front of the 1. Interference just says that elements of a superposition representing the same bit string, but with opposite amplitudes must cancel. So here's an example. If we apply the Hadamard to a uniform superposition over 0 and 1, we expect to get 0. And you can see that because of linearity, because this is the same as applying the Hadamard first to 0, getting 0 plus 1, then applying it to 1, getting 0 minus 1, and the two ones cancel. Now, what if we tried to use classical homomorphic encryption in the most obvious way to encrypt quantum data? So what if we took each of these 0s and 1s and we just encrypted it with the classical homomorphic encryption scheme? So we get something like this. Now here's where the probabilistic encryption becomes really troublesome, because these two encryptions of 1 will very likely be different. And so what that means is that they will not cancel with high probability. And this is why, so the most obvious way of using classical homomorphic encryption schemes for quantum circuits doesn't work. I'm not giving you a full implausibility result. I'm just giving you a sketch of why it's difficult to immediately apply classical homomorphic encryption schemes to quantum circuits. Now, because of this difficulty, or maybe in part due to this difficulty, quantum homomorphic encryption scheme has been studied in a slightly weaker setting, in which the client is quantum rather than classical. So remember, when I first presented it to you, I said, we'd like a classical client to be able to delegate a computation to a quantum server. And the model was weakened. In previous work, the model was weakened to allow a client with a very small amount of quantum capability. So we were trying to work towards classical by first restricting the quantum capabilities of the client. And as far as I know, this question was first studied by Andrew Childs in 2005, in which he said that this blind computation, meaning privately delegating a quantum computation, was possible with the quantum client information theoretically if interaction was allowed. So what this means is that you have a quantum client interacting with a quantum server, and the client can delegate a computation to the server privately, meaning the server learns nothing about it, as long as the two can interact. And moreover, the security is information theoretic, which means we don't have to assume any bounds on the power of the server. So no matter what the server does, he cannot learn about which computation he's applying.
Can I ask a question?
Yeah.
So what do you mean by interact? You mean it's there must be more than like one message? Like you always have to interact, like once, twice. You're saying you need to do it more than once or something?
Yes, exactly. So interaction means there are multiple rounds of interaction. And when I say non-interactive, it just means the client sends over one message, the server sends over the outcome of the computation, and you're done. But you're right, that's confusing because both of them require interaction. Okay, so this was first shown to be possible by Andrew Childs. And since then, this work has been improved tremendously, meaning the client was reduced to a very small amount of quantum capability. So really all the client had to be able to do was hold a single qubit register, and he had to be able to manipulate this qubit and send it over to the server. And just this very tiny amount of quantum capability was shown to make information theoretic blind quantum computation possible. And then this result was further improved. So even with the single qubit quantum register, polynomially many rounds of interaction were still required. And then this result was further improved by Delac, Schaffner, and Spielman, where they got rid of the interaction by introducing computational assumptions. So they said, you can get rid of the interaction, but now we have to assume that the quantum server cannot break learning with errors. So as long as he can't break learning with errors, he can't learn about the data, but if he can break learning with errors, then the security of the data is compromised. And for those of you who don't know, learning with errors is just a computational problem referring to the difficulty of solving noisy linear equations. I'm not going to get into it much in this talk, but I will be frequently referring to the assumption that quantum computers cannot break learning with errors. And that's a widely known assumption. We don't know how to prove it, but I think most people believe that it's true. So that's all I'll say about that. Okay, so this work was great. This line of work with the quantum client was great because it introduced a lot of new techniques to the field of delegated quantum computing. However, there is a major problem with these results. So let me try to describe to you what it is. In all of these results, the reason that the client has to be quantum is because the client creates something called quantum evaluation keys. And these are small quantum states, which he sends over to the server. And the server uses these keys to help him privately evaluate the quantum circuit. So as the server is homomorphically applying these computation, he's using up these quantum keys. And the number of keys corresponds to the size of the circuit, of the delegated circuit. And moreover, since the server is using these quantum states to perform the computation, the keys aren't reusable because they're quantum states. Now, if you put all this together, what I'm saying is that each time the client wants to delegate a quantum computation, he has to create some number of keys which corresponds to the size of the circuit. And this has to happen each time because these keys aren't reusable. So what's happening is that this client is weaker than the server in the sense that he's running smaller quantum computations, but the size of the quantum computation still corresponds to the size of the circuit he wants to delegate. So in some sense, this isn't really answering the question of what we wanted in homomorphic encryption. What we wanted there was we wanted a very weak client to be able to delegate a computation to a much more powerful server. So the client shouldn't be doing some amount of work corresponding to the size of the circuit. So that's why it's really important that we go back to the original question with a classical client and a quantum server. Because here you don't have this issue of reusability of keys, because everything the client is sending over is classical, so these are inherently reusable.
So can I ask one more question?
Yeah.
So right, so there were these two things, U and M, and you said that, U can be basically absorbed into M, but is there maybe because of this kind of interference issue, could it be that we can just classically homomorphically encrypt U but not M in some way? Because maybe, I feel like U is a sort of, maybe it's wrong, but it feels like there are two pieces of data and maybe one of them could potentially be could potentially not suffer from this interference problem, but the other one does. Maybe it's totally wrong.
I'm not following. So why would something not suffer from the interference problem?
Because U is sort of the circuit we're applying, while M is the message. I'm thinking of M maybe in some sense a quantum state. That's okay, maybe it does make sense. Don't worry about it. I thought that maybe one is easier than the other. Don't worry about it. Okay, it's maybe a bad idea.
Okay. Okay, so let's continue. So I want to go back to the variant where the client is purely classical because it's strictly stronger than, in some cases, it is strictly stronger than if the client is quantum because we don't suffer from these issues about reusable keys. Now, what I'll show you in this talk is that certain classical homomorphic encryption schemes can be used to homomorphically evaluate quantum circuits. So what this means is that the classical client, there are certain classical homomorphic encryption schemes for which the classical client can use this encryption scheme to encrypt his data, send it over to the server, and the server can now homomorphically apply a quantum circuit. And this might be confusing because earlier in the talk I said that there's this interference issue which makes it difficult to use classical homomorphic encryption schemes to evaluate quantum circuits. And what I'll show you is that there is a different way to use classical homomorphic encryption schemes to evaluate quantum circuits. So it's not the most naive way that I discussed earlier. So using this different way, it is possible to use classical homomorphic encryption schemes to evaluate quantum circuits. And just as a brief note for those of you who have heard of classical homomorphic encryption schemes before, because I'm just using them directly to evaluate quantum circuits, I inherit the same advantages. So for example, the keys are immediately reusable because they're classical. There's also something that's used in the classical world, and it's an assumption. And if circular security is assumed, it means that the amount of work the client has to do to delegate the circuit is completely independent from the size of the circuit. So that's a pretty huge advantage in comparison to the previous schemes where the client had to do some amount of work corresponding to the size. And if you take away this assumption of circular security, then the amount of work the client has to do corresponds to the depth of the circuit, but the client only has to do it once. And then the server can run any number of computations as long as they have the same depth. Okay, so this is the difference between the previous schemes. And this scheme is the first to allow blind quantum computation between a classical client and a quantum server, because the previous schemes all required either a quantum client, or there were some restricted schemes which allowed a classical client but either didn't have security or couldn't be used for universal quantum circuits. So far I've told you what I'll be telling you in this talk, and now I'm going to get into the actual result. And before that, does anyone have questions on the setup? Okay, so to start, I'm going to tell you about the encryption scheme that the client will use to send over his data to the quantum server. This is called the quantum one-time pad, and it's also known as the Pauli one-time pad. And it's a method of information theoretically encrypting quantum states. So let's say psi is our starting quantum state, and let me tell you what the encryption looks like. The first thing is to sample a bit z at random. And then apply the Pauli phase operator to the quantum state. So if z equals 0, nothing happens. If z equals 1, a phase of -1 is inserted. The next step is to sample a bit x at random and apply the x Pauli operator to the quantum state. And the x Pauli one-time pad is the same as the classical one-time pad, meaning if x equals 0, nothing happens. If x equals 1, then each bit is flipped. So 0 is flipped to 1 and 1 is flipped to 0. Now, if you put both of these together, this is a method of information theoretically encrypting a quantum state, because if you look at this output state, the state psi with a random Pauli operator applied to it, it's maximally mixed. There's nothing, if you just look at that output state and you don't know x and z, you have no information about the quantum state. So this is an information theoretic method of encryption, meaning regardless of how powerful some adversary is, he cannot tell anything about the quantum state. And now I'm going to weaken this to be a computational encryption, meaning I have to assume that the quantum computer cannot break some problem in order to prove security. And the reason I'm weakening it, so this might seem strange because I gave you a strong encryption scheme and now I'm weakening it to something with computational assumptions. The reason I'm doing that is because by weakening it, we're going to allow for homomorphic operation of the encryption. So this is a computational version. Now, you still have the one-time padded state, which is a quantum state, but the classical encryptions of the one-time pad keys are included as part of the encryption. And these bits z and x are encrypted using a classical homomorphic encryption scheme. So this computational encryption is a two-part encryption with a quantum state and classically encrypted keys. And so this is the full encryption scheme that we'll be using in the quantum homomorphic encryption scheme. So the classical client encrypts his data with this computational Pauli one-time pad and sends it over to the server. And just so one note here, it might look like the client is sending over a quantum state, which is confusing because I said that the client was classical. But the only thing to note here is that as long as the input data is classical, so meaning if psi is a standard basis state, then this one-time padded state is just this classical string, let's call it M XORed with X. So as long as psi is a standard basis state, then the one-time padded state is still a standard basis state, and therefore it's classical information.
could I just clarify that? So when
Yeah.
you're applying a Z operator, you're changing the phase, right?
Yes.
But that is something that you're saying that the classical client can do.
Well, no, because if the input psi is a standard basis state,
Ah,
then the phase operator does nothing, so you can ignore it.
okay.
Yeah. Okay. Okay, so this is how the client sends over his information. He encrypts it using the computational one-time pad. Now, the next thing I have to tell you is how the server can homomorphically apply a circuit on top of the encrypted data. So the server is supposed to apply some circuit U to psi, but psi is encrypted. And how it works is that the quantum homomorphic computation boils down to two parallel computations. So the server will apply a classical homomorphic computation on the encrypted classical keys. And in parallel, he'll apply a quantum computation to the one-time padded state, which is dependent on the classical keys. This is kind of the crux of the issue, the fact that at some point in the homomorphic computation, the server will have to apply a quantum operation to the one-time padded state, which is dependent on the classically encrypted keys. And this was known in all previous work. So in previous work, everyone used the fact that quantum homomorphic computation boils down to these parallel computations, and that the crux of the issue was this quantum operation, which is dependent on classically encrypted keys. The difference was in that previous work, the client sent over a quantum state with some hidden information in the quantum state. And that hidden information allowed the server to take these classically encrypted keys and convert them into a quantum operation. And what I'll show you is that actually those quantum states are not required. The server can just look at this classically encrypted data, and somehow he can take this classically encrypted data and convert it into a quantum operation. And so for the rest of this talk, I'll ask you to take it on faith that the crux of this problem of homomorphic computation is this conversion of classically encrypted information into a quantum operation. I'm not going to tell you exactly how that reduction works, so I'll just ask you to believe that the hard part of quantum homomorphic computation is this dependent quantum operation. And for the rest of this talk, I'll tell you how that operation works. So how the server can take as input classically encrypted keys and apply a quantum operation which depends on those keys. And in the next step, I'll define exactly what that means, what it means for him to take in classically encrypted keys, apply a dependent operation. So before that, are there any questions?
So the first thing that you need to do, right, is you first need to make sure that you're not encoding any unitary. The only thing you're encoding is the state, right? You're still doing this thing, right, where all of your input is in the message, right? That's still the first step, right? And then this X and Z, I mean, that's a cartoon. In reality, you have like many of these quantum states, and there are many X's and many Z's, or?
Exactly.
Okay.
So what I showed you is how to encrypt a single quantum state, which is just with the single bit X and Z. But if it's an n qubit quantum state, then X will be an n bit string and Z will be an n bit string.
Right. And all of your input is in that state. You don't need to encode the unitary because you did this clever mapping,
exactly.
Right?
Yeah. So this string will include both the input message and kind of the control bits for each gate in the circuit. Okay, so now that I've told you what I'm going to focus on this conversion from classical ciphertext to quantum operations. Now let me define what that means, and then I'll spend the rest of the talk telling you how to perform that operation. So I'm going to call this operation the encrypted C naught operation. And this encrypted C naught operation is the core of the homomorphic encryption protocol. And what it is, it's a means of the server taking as input classical ciphertext and applying a quantum operation dependent on those ciphertexts. So the quantum operation that he will apply is called the C naught gate. The C naught gate is a reversible XOR gate. So what it does is it takes as input 2 bits, A and B. The first wire is unchanged, and it's used as the control wire for the second. So it's XORed into the second register. And I've written this diagram with bits, but in general, these bits will be in superposition. Now, what the server needs to do is take as input a bit S encrypted under a classical homomorphic encryption scheme, and conditionally apply the C naught to an arbitrary 2-qubit quantum state dependent on this bit S. So here's what it looks like. So now the first wire is some classically encrypted bit S. Now he only applies the C naught if S is equal to 1. So if you look at that last wire, if S is equal to 0, nothing happens, B is unchanged. If S is equal to 1, the C naught is applied. And in the last line of this slide, I've just written out what this looks like in superposition. And again, this operation is what the entire homomorphic encryption scheme boils down to. And so this operation is quite interesting because what's happening is that the server is taking as input a classical ciphertext, and he's conditionally applying a quantum operation even though he can't see what's in the ciphertext. He can't see what the bit S is, but somehow he's supposed to be able to either apply the C naught or not based on the bit S. So as I've written it, the first thing to note is that this is impossible because I said that he should be able to apply it to an arbitrary 2-qubit quantum state. So let's say we set A equals to 1 and B equals to 0. Then if he can do this, the second register will just contain S, which means he's broken the classical homomorphic encryption scheme. So this is impossible as I said it, but I'm just going to change it in just one way, and I'll say that the output state should be suitably encrypted. And what I mean by that is that the output state will be encrypted with the computational Pali one-time pad. And it turns out that if the output state is encrypted, then this operation is possible. So let me just recap what I just said. So what I've told you is that quantum homomorphic computation boils down to two parallel computations: a classical homomorphic computation on the encrypted Pali one-time pad keys, and a dependent quantum computation. So the quantum computation is dependent on the classically encrypted keys. Then I defined this operation formally. I called it an encrypted C naught operation. In this operation, the server takes as input the encryption of a bit S, an arbitrary 2-qubit quantum state. Now he's supposed to conditionally apply C naught to the quantum state, and he's going to output the encrypted version. So he conditionally applies the C naught, but the output is encrypted with the computational Pali one-time pad. So he outputs the one-time padded quantum state, as well as the classically encrypted one-time pad keys. So this is a full encrypted C naught operation. And in this talk, what I'll show you is that certain classical homomorphic encryption schemes can be used for the encrypted C naught operation, which means that they can be used to homomorphically evaluate quantum circuits. Because as I told you before, the entire quantum homomorphic computation really boils down to this encrypted C naught operation. And what I mean by this is that if a classical homomorphic encryption scheme has certain properties, then the server can take it as input and convert it into the C naught operation. So this doesn't hold for all classical homomorphic encryption schemes. It holds for certain ones. And at the end of the talk, I'll tell you what kind of properties the classical homomorphic encryption scheme has to satisfy in order to make this conversion possible. The next thing I'm going to do is I'm going to build the encrypted C naught operation. And to do that, the first thing I'll get into is a cryptographic primitive called trapdoor claw-free functions, because these are crucial in building the encrypted C naught operation. Now, before I get into the construction of this operation, are there any questions so far?
Yeah, can I ask a question here? I feel like I'm missing something about the setup. So, I mean, I guess all the way along, like the state will be encrypted, and client will hold some keys. And so, if you want to do a Clifford operation like a C naught, isn't it possible for that to effectively done just by sort of like updating the keys? Like I feel like somehow the hard thing to do should be to do some non-Clifford operation.
Yeah.
So why somehow are we focusing here on the C naught, which seems like
okay? So you're exactly right. The Cliffords are easy and non-Cliffords are hard. But if you notice, the C naught that I'm doing is not a Clifford because it's controlled on a bit S.
Oh, I see. It's controlled, and the S could be somehow in quantum superposition. Like
no, it's just so as soon as you add a control bit, it's not a.
I see. Even though it's something classical, actually somehow it's effectively non-Clifford. It's like doing a Toffoli game. Yeah.
So let me just tell you a little bit more about that. So what you said is right. So Cliffords can always be done easily, essentially because you can apply a Clifford on top of a one-time pad and push it past. All it does is change the one-time pad. So all you need to do is homomorphically update the keys. If you try to apply a Toffoli and push it past the one-time pad, what happens is you'll have corrections, which are essentially C0 operations, which are dependent on the one-time pad keys. So to finish the Toffoli operation, you'll have to apply a C0, which is dependent on encrypted information, the one-time pad keys. And that is exactly what the encrypted C0 operation is. It's applying a C0, which is conditioned on encrypted classical information.
Got it. Okay, thanks a lot.
So that's exactly where it comes from, the Toffoli. Okay, are there any more questions on the setup before I continue to the construction of the encrypted C0? Okay, so let's start with the encrypted C0. And to do that, let me first define what trapdoor claw-free functions are. So these are, this is a cryptographic primitive that's been very well used in classical cryptography. And they were first defined by Goldwasser, Macaulay, and Rivest in 1984. And a trapdoor claw-free function pair is a pair of functions f0 and f1, which are injective, and they have the same image. The claw-free property says that it's computationally difficult to find a claw. A claw is a pair of preimages which map to the same point. So the claw kind of refers to this picture. And when I say it's hard to find a claw, I mean that for either a quantum or classical machine, if all they're given is public access to the function, so they're able to evaluate f0 and f1, then it should be hard to find any claw, any pair of preimages which maps to the same point. Meaning if this machine can find a claw, it can break some underlying computational assumption. So it can break some hard problem. And in my case, the hard problem that I'll be referring to is always learning with errors.
And could I just clarify, when you're talking about public access, is that Oracle access, or do they actually see like the algorithm that computes f0 and f1?
Yeah, there's actually a circuit to compute f0 and f1. It's not Oracle access.
Okay, thanks.
Yeah. Okay, so that's what the claw-free property means. The final property I need is a trapdoor. The trapdoor is some string which allows for efficient inversion. So what this says is there's an algorithm which can take as input a trapdoor in any of the images y, and it can output the two preimages of y. Now this might be a little confusing because first I said it's hard to find a claw, then I said with the trapdoor you can find every claw. So what I'm saying is that without a trapdoor, so if a quantum or classical machine only has access to the evaluation of the functions, that machine cannot find even one claw. But if an efficient machine has access to the secret trapdoor, which isn't given out as part of the public evaluation process, then this machine can invert both functions efficiently. So I need both of these properties. Now, these have, as I said, these functions have been very well used in the classical world, but it turns out in the quantum world, there's something very interesting that happens. So quantum machines have this unique capability where just given access to public evaluation, so all the quantum machine can do is evaluate f0 and f1, the quantum machine can sample a random image y and create a uniform superposition over the corresponding claw, so over the two preimages of y. And just as this is written, it might look strange because I just said that the quantum machine should not be able to find a claw, but I said that it's easy for a quantum machine to sample a superposition over a claw. So the thing to note here is that, yes, it's easy for the quantum machine to do this, which I'll tell you about in a second, but this doesn't imply that the quantum machine can find both x0 and x1, because x0 and x1 are stored in superposition. So the quantum machine would have to measure it, and it turns out when he measures the superposition, he gets some interesting information, which is not possible classically, but it's not enough to actually break the claw-free assumption. So now let me tell you how the quantum machine creates the superposition, and then I'll go back and just discuss this state a little bit more, the superposition over the claw. So here's how the quantum machine does it. It's pretty straightforward. All the quantum machine does is he first creates a uniform superposition over the domain. So B is a single bit, and X is the domain of the functions f0 and f1. Then the quantum machine applies the classical functions in superposition. So dependent on the bit B, he either applies f0 or f1. Now the quantum machine measures the last register to obtain an image y. Once he measures that last register to obtain an image y, the remaining registers have to collapse to the values that are consistent with y. Since f0 and f1 are both injective, this means for both values of b, so for b equals 0, there's only one value of x remaining, which is x0. For b equals 1, there's only one remaining value. So as a result of measuring y, the state collapses to this uniform superposition over the two preimages of y. So this is really easy for the quantum machine. All he's doing is he's evaluating the function in superposition and measuring. Okay, so let's go back to the state. Like I said, this is a uniquely quantum capability because he's storing some hard to find information, which is the claw, in superposition. And this unique quantum capability was used in previous results for different applications. So it was used to generate randomness from quantum machines, and it was also used to classically verify quantum computers. And in this setting, it's used for a totally different purpose. And what it does is it essentially allows a quantum machine to store a classically encrypted bit in superposition. So it allows a quantum machine to take a classical encryption and take this information and convert it into a superposition. This is exactly what I need for the encrypted C naught operation. So the next thing I'm going to show you is how trapdoor claw-free functions enable the encrypted C naught operation. Before I get into that, are there any questions on trapdoor claw-free functions or anything that came before this? Okay, so let me move on to showing you how trapdoor claw-free functions make the encrypted C naught operation possible. To do that, I'll first remind you what the encrypted C naught operation is. It's an operation which enables a quantum server to take as input a classically encrypted bit, S, an arbitrary 2-qubit quantum state, and conditionally apply the C naught operation to the 2-qubit quantum state based on the bit S, and he'll output the computationally one-time padded version of the output state. Now, what I'm going to tell you now is that if a bit S, so remember the server takes as input the encryption of a bit S, and I'll say that if the bit S is encrypted using a trapdoor claw-free function pair, and I'll define exactly what that means in a second, then the encrypted C naught operation is very easy. And remember, this isn't what I told you initially. What I told you initially was I want the encryption of the bit S to be under a classical homomorphic encryption scheme. So here I'm taking an intermediate step where I'm saying it's not under a classical homomorphic encryption scheme yet. It's a special encryption having to do with trapdoor claw-free function pairs. Then in the last step of the talk, I'll link this. So I'll take this special encryption and I'll link it to classical homomorphic encryption schemes. So right now, let me define what I mean by the encryption using a TCF pair. So here's what it is. The TCF encryption of a bit S is just going to be a TCF pair. So the encryption is just a pair of trapdoor claw-free functions, F0 and F1. Now, here are the properties of the function pair. So the first thing I've done here is I just split up the domain so that the first part of the domain is a bit. And now the next two properties are just saying that this function pair is a trapdoor claw-free pair. So you have injective, same image, trapdoor. It's hard to find a claw. And I've just broken up the claw so that mu0 and mu1 are bits and r0 and r1 are strings. So far, all I've said is that the TCF encryption of a bit S is a trapdoor claw-free function pair F0, F1. Now this last property is what makes it the encryption of the bit S. And what this says is that for all claws, the first bit of the claw hides the bit S in the XOR. So for all claws, mu0 XOR mu1 equals S. So this last property is what makes this the encryption of a bit S, because this TCF pair is really hiding the bit S in the XOR of each claw. So this is just a definition of what it means to use a trapdoor claw-free function pair to encrypt a bit S. So this is just some specialized encryption.
Ask a question. Sorry, I thought we needed a sort of F0. I thought was going from a like I thought that like there must be one F0 and F0 must map to Y and F1 must map to Y. But here, like in the previous, like when you define this claw-free function, it looked like there was like a 0 and F0 and then 1 and F1 that map to the same thing. But now you're saying that could be like cases where you have a 0 as the first bit and they both map to the same. Like I always thought that a claw always had a 1 0 and 1 1, like drawn here, right? Like 0 x 0 and 1 x 1. So I feel like there is nothing to encode. It looks like it's always 0 plus 1 is 1. So S is always.
Sorry, that's confusing. So the claw here, The claw is not 0x0 and 1x1. The claw is just x0 and x1.
Okay.
So the claw doesn't, here, like the domain is just x0 and x1. There wasn't an extra first bit there.
I see. So you introduced this extra, the 0, 1 has nothing to do with the 0 and
No.
1 and the subscript of F0 and F1.
Exactly.
Okay,
So
I get
if
it.
the 0 and 1, the reason it came up is because of this bit b, which tells you which of the two functions to apply.
Right, and this B has nothing to do again with that 0 and 1 that you defined in the next, oh, I see, I was confused. Okay, got it. Okay, and maybe since I interrupted you already, one more question. So when you, can you go forward a little bit? More, yeah, here, this previous slide, previous slide. Yeah, this one. So I thought that, like, I'm surprised that the input is psi. I thought the input before already had the X and the Z applied on them. Why did they move to the right?
No, so in the pictures I showed you before, it was like this. The input is always an arbitrary 2-qubit quantum state.
Well, but when we were discussing, like, what does the client give to the server, I thought, like, and Carl asked that question, you know, I thought the client is already sending the state psi with X and Z applied, but now you're saying the server applies them.
No, okay, so you're right that this state psi will be encrypted. And the reason that I didn't include this is because, so sure, in the general scheme, when the server applies the encrypted C naught operation, the input will also be encrypted. But I was just trying to encapsulate what I need here for the encrypted C naught operation. And for the encrypted C naught operation, I don't really care about whether the input is encrypted or not. The encrypted C naught operation is really just about saying he's taking an encrypted bit S and he's converting it to a quantum operation. But you are correct that in the actual scheme, this will be encrypted.
Okay, sorry for interrupting the flow. Thanks. Sorry.
No, that was confusing. Thanks for bringing it up. Okay, so what I did here was I defined what it means for a trapped or a clock-free function pair to encrypt a bit S. So now the encryption of the bit S is just this function pair F0 and F1. And now I'm going to tell you how to apply the encrypted C naught operation with this special encryption. And it turns out that this operation is actually very easy. So let me go through the full details of telling you how to apply the encrypted C naught operation with this special encryption. So remember our goal. The server is given the encryption of S, which is now just this trapped or clock-free function pair F0 and F1. And he wants to conditionally apply C naught to an arbitrary 2-qubit quantum state. And he'll output the encrypted version with the Pali onetime pad. So just to simplify things for the presentation, I'm going to set B equals to 0. That's all. And when you want to generalize, this is pretty straightforward. I just did this so I have one less parameter floating around. Okay, so here's how it's done. So this is the goal. Given the encryption of S, compute the encrypted C naught. What the server will do is, using the encryption of S, which is F0 and F1, he's going to sample a random Y and entangle the state with the corresponding clock. This is exactly what I showed you before. So he takes his state, which is this alpha AA, and he entangles it with a claw mu0 R0, mu1 R1. The way he does this is just how we did before. He creates a uniform superposition over the domain of the function, and he applies either F0 or F1 in superposition depending on the bit A. He measures that final register to get an image Y. As a result of the measurement, the mu R register collapses to the two pre-images consistent with Y. So this is all the same thing that I showed you before. Now the interesting thing comes in because F0 and F1 was the encryption of the bit S, which meant that for mu0 and mu1, they hide the bit S. So mu0 XOR mu1 equals S. So what he's done is now he has S in superposition. To see that, I can rewrite the above state. So let's break this down. If A equals 0, then this register mu0 XOR A.S is still just mu0 because A equals 0. If A equals 1, then you get mu0 XOR S, which is actually equal to mu1. So these second and third equations are equivalent. But the reason I wrote it in this way was to show you that when the server entangled the state with a claw, he took the bit S and he put it in superposition. So now if you compare this to the top line, we're very close to our goal. We have A dot S, but then we have these other parameters, mu0, R0, and R1, which are kind of masking the information and we need to get rid of them. Now it turns out that this masking is actually crucial because this is what makes it possible. So this information, this mu0, R0, and R1, can be turned into Pauli one-time paths. So mu0 is just an X Pauli operator, it's just a bit shift. Now R0 and R1 are a little more complex, but to get rid of them, all you have to do is perform a Hadamard transform on the R register and measure, and then they turn into phase operators. So really this extra information that prevented us from the state from looking exactly as we wanted is they're just the Pauli operators, the Pauli encoding. So that was really fast. Let me just recap everything that I just said. The server wants to perform this encrypted C naught operation, which is the conversion of a classically encrypted bit into a C naught operation. In the setting that I told you, this encryption of the bit S is the special trapdoor clock-free encryption. To do this, the server uses the trapdoor clock-free function F0 and F1 to entangle the input state with the claw. Then, since the claw has the special property that mu0 XOR mu1 is equal to S, just entangling the input state with the claw is actually putting the bit S in superposition. The final thing to note was that this extra information, mu0, R0, and R1, serve as Pauli one-time paths. So mu0 is a classical one-time path because it's just this XOR operator. R0 and R1 intuitively are needed because you have a superposition, so they kind of hide the phase information about S. And this is just a calculation, and to turn them into Pauli Z operators, all you have to do is perform a Hadamard transform on this register and measure the register, and then you get some phase operator, which has to do with R0 and R1. Now, so this is the full encrypted C naught operation. And now I'm going to recap everything I've told you up till now. But before that, are there any questions on the encrypted C naught?
Right. So is this the state that you're sending it? Is it a single A is actually a single bit?
Yeah. So remember, in general, this was a superposition over A and B. But I said I was just going to simplify and set B equal to 0.
Oh, I forgot. Oh, yeah. Okay, fine. So that's why it's a C naught. It's like, oh, that's a single qubit. What happened? Okay,
Yeah.
I forgot. Right. Okay.
But when you add B in, nothing really changes. Yeah.
And so the information, maybe this is coming up in the next slide, but so the information about these bits, mu0, R0, R1, the quantum server doesn't necessarily know these bits, but has an encryption of them. Is that the idea?
Exactly.
That's what we end up with? Okay.
So that's the classical homomorphic in computation. So he can use a classical homomorphic computation to compute these keys and update them.
I see.
Yeah. Okay, so this is the encrypted C naught operation. So now let me tell you everything that I've told you so far. So the first thing I told you was that this is what I asked you to take on faith, that homomorphic computation of quantum circuits boils down to a parallel computation, a classical homomorphic computation, and a dependent quantum operation. And the quantum operation is it depends on the classical keys, and what it is the server's ability to convert a classical ciphertext into a conditional C naught operation. I call this operation the encrypted C naught operation, and I defined it formally using this picture, where the server takes as input the encryption of a bit S, an arbitrary 2-qubit quantum state, and he outputs the computationally one-time padded result of conditionally applying the C naught to the 2-qubit quantum state. And what I just told you is that if this encryption of S is special in that the encryption of S is a trapdoor claw-free function pair, which hides the bit S in each claw, then this conversion is really easy, and all the server has to do is entangle his state with the claw. And just by this process, he's completed the encrypted C naught operation. Okay, so now I need to go back and link to classical homomorphic encryption schemes. So remember, when I first presented this operation, I told you that the encryption of the bit S has to be under a classical homomorphic encryption scheme. The reason this was necessary is because the server is doing these two computations. He's doing a classical homomorphic computation and a dependent quantum computation. And to do the homomorphic computation, this encryption of S has to be under a classical homomorphic encryption scheme. And so far, what I've shown you is that this is possible if S is encrypted using a trapdoor claw-free function pair. And now we need to link the two. And the way to link it is by asking are there classical homomorphic encryption schemes for which the encryption of S is just a trapdoor claw-free function pair. Alternatively, I can say, given the encryption of S under a classical homomorphic encryption scheme, is it easy to produce the TCF encryption? So is it easy to produce the public description of functions F0 and F1 for which each claw hides the bit S? So what the server is doing is he's taking as input the encryption of S under a classical homomorphic encryption scheme, and he's converting it to this special TCF encryption. Now he can easily perform the encrypted C naught operation. So if the classical homomorphic encryption scheme allows this conversion, then we're done. He can use this homomorphic encryption scheme to evaluate quantum circuits. So it turns out that the answer to this question is yes. So there are certain classical homomorphic encryption schemes which allow this conversion, but they have to satisfy certain requirements. These requirements can be formalized to define something called quantum-capable classical homomorphic encryption schemes. These are classical homomorphic encryption schemes which allow the conversion from the input encryption to the TCF encryption, thereby allowing homomorphic evaluation of quantum circuits. And the final thing to note is that there does exist a quantum-capable classical homomorphic encryption scheme, and it can be created by combining existing schemes in classical cryptographic literature. So for the last part of this talk, I'm going to try to give you a bit more intuition about these requirements. So I'll try to tell you exactly how the server takes as input the encryption of a bit S under a classical homomorphic encryption scheme and produces F0 and F1. Before that, are there any questions? Okay, so now let's get into constructing these, how the server can construct these functions F0 and F1. So let me just remind you what the TCF encryption of a bit S is. It's a trapdoor claw-free function pair F0 and F1, for which the first bit of each claw hides S in the XOR. Okay, so now I'm going to define F0 and F1, how the server would define it. So the first thing is that classical homomorphic encryption schemes typically have a public encryption mechanism. So what this public encryption does is it has some public key, and then it takes as input a bit, let's call it mu, some randomness r, and it outputs the encryption of the bit mu under randomness r. And that is exactly what F0 will be. F0 will just be the public encryption function. So it takes as input a bit mu, randomness r, outputs a ciphertext encrypting mu with randomness r. This is a public function, so it's already defined. The server has to do nothing here. Okay, and what F1 is it's F0 shifted by the homomorphic XOR of the ciphertext, the encryption of S. This is where the encryption of S is used. So to compute this, the server has input mu1 R1. He first applies F0 to compute the encryption of mu1 under R1. Then he homomorphically XORs it with the encryption of S to get a new ciphertext, which encrypts mu1 XOR S. So this is also easy for the server to compute because it consists of F0 along with the homomorphic XOR, which is easy for him to do. Now I've defined F0 and F1, but I need to tell you why these TCF encryption properties are satisfied. So why F0 and F1 constitute a TCF pair which hides the bit S. So let's start with hiding the bit S. This is the easiest property. This property follows by definition because F1 is just F0 shifted by the homomorphic XOR. So if the two match, if the two ciphertexts match, then mu0 XOR mu1 has to equal S. Okay, and then this property implies the claw-free property because since each claw hides the bit S, if an adversary finds the claw, he finds S, thereby breaking the classical homomorphic encryption scheme. Now, the next thing I need to tell you is the trapdoor. And this has to do with properties of classical homomorphic encryption schemes. So for all classical homomorphic encryption schemes, there are secret keys which allow an efficient algorithm to look at a ciphertext and use the secret key to encrypt the bit that is to extract the bit that is encrypted in the ciphertext. There are other schemes with an additional trapdoor which allows for randomness recovery. So this additional trapdoor allows an efficient algorithm to look at a ciphertext and extract the randomness which was used to construct the ciphertext. So if my classical homomorphic encryption scheme has this randomness recovery property, that's enough for me, because then this randomness recovery property will allow us to encrypt both the randomness and the bit that was encrypted, which is the same as inverting these functions f0 and f1. Okay, and then the final property is the tricky one. And sorry, this trapdoor property implies that the functions are injective. This final property is that the two functions f0 and f1 have to have the same images. This is tricky because when you shift by the homomorphic XOR, you kind of shift the images. So we do have to weaken the requirement so that instead of saying that you have the same images, we weaken it so that you say you have some distribution over the domains so that the corresponding distributions over the images are statistically close. I'm not going to get much more into that. All I'll say is that this is possible to formalize. And so if you formalize these requirements, then you can define this thing that I called quantum capable classical homomorphic encryption schemes, which are schemes which allow this conversion from the encryption of S to a trapdoor claw-free encryption, thereby allowing homomorphic evaluation of quantum circuits. And the final thing that I mentioned earlier was that you can construct a scheme which satisfies these requirements by combining two existing schemes in literature, two existing classical homomorphic encryption schemes. So now let me just recap everything I told you. I started by asking you to take it on faith that the quantum homomorphic encryption boils down to something called the encrypted C naught operation, which is the ability of the server to convert a classically encrypted bit into a quantum operation. Then I told you that if the bit is classically encrypted using a trapdoor claw-free function pair, then this encrypted C naught operation is really quite easy, and all the server has to do to complete it is to entangle his input state with the claw. And this suffices to take a classically encrypted bit and store it in superposition. Then I needed to link back to classical homomorphic encryption schemes. So I needed to make it possible for the server to take as input a classically encrypted ciphertext and convert it to a TCF encryption, which would enable him to perform the encrypted C naught. And I told you that this is possible if a classical homomorphic encryption scheme satisfies certain requirements. And I called these schemes quantum capable. Finally, such a scheme does exist in literature, and it's under the assumption that quantum computers cannot break learning with errors. So putting all this together, I'm telling you that blind delegation of quantum computations by a classical client is possible, assuming that quantum computers cannot break learning with errors. So that's all I have for this talk. Thank you for listening.